This brings us to hydrodynamic thermal flow maps. This is a way to determine if there are what are called circumferential anisothermalities in horizontal fired heater tubes, or really any tube. It is a way to take a flow regime and put it against a hydrodynamic map and say, these areas we're worried about flow, these areas we are not. Why is this important? Because if your tube isn't the same temperature all the way around, if there's a hot point on top, that hot point is going to want to expand, you'll get stress, and it'll actually bend the tubes. We were looking at a fired heater the other day where all of the tubes were bent and arced up off of the tube supports so that they were impinging on the tube supports above them. That's a problem. You don't want that kind of contact. So what is the answer there? How do we find the answer? So a hydrodynamic thermal map is basically just a hydrodynamic chart that has, bubble and intermittent, wavy, and annular. Basically that chart with an overlay of some other information that gives us the anisothermality of that diabatic condition. And it requires a multidiscipline approach. Mechanical engineering needs to do the heater tool to give you a much better indication of the heat transfer going inside that tube. And it's almost done on a tube-by-tube basis. Usually that's what we recommend. On a tube-by-tube basis, you take the heater information from mechanical and you put it into a process simulator, and you iterate back and forth until you have a very good profile going down between them. The reason you need to do this is that process simulators aren't really good at knowing the geometry of heaters and others, and process simulators aren't really good are figuring out whether cracking is going on. Cracking is actually a big issue because FRNC won't figure out cracking. They'll say, okay, this thing is all one phase here, but we haven't taken into account cracking, which is thermal cracking probably going on inside of that. Thermal cracking means now there's vapor that we didn't expect to be there before. Going back and forth between the two, you can come up with a relatively quick, easy answer to what is really going on inside these tubes. So a client had tube rupture in the convection section. What was going on here? There's a little bit of H2S there, but we expected it to be all liquid. What's going on? And so hydrodynamic thermal flow maps yielded some insight. But this was their conditions at failure. And in this convective section, this dashed line is their convective section, that was all anisothermal. There was hotter spots on the top of the tubes than on the bottom of the tubes. Yet when they came into their radiant section, they didn't have any problems in the radiant section. It was just in their convective section. So how do you fix that? Well, one is to reduce the tube diameter, make things go faster. If we improve the gas velocity, we move out of the region this way, and we improve the liquid velocity, we move out of the region that way. That's one way to fix it. And that actually appeared to do what we needed to do. It moved up the liquid velocity, in particular, up out of the region, reduced tube diameter, which is actually often the case. Often, refineries will increase their tube diameter in their heaters to this effect, and then wonder why things aren't working. And they end up going back to the design diameter of the fired heater to fix this kind of issue. Another way would you inject velocity steam. Velocity steam pushes the vapor, and it actually pushes you out of the region this way, but then you're heating up mass that you don't really need to be heating up. There are different ways to look at this from either side, but what is best for the client, and that's that.